In this work, we present a unified Stokes solver featuring a polynomial reduced fluid representation for improved computational efficiency. Simultaneous solution of stress and pressure forces are necessary for accurate simulation of strongly viscous liquids, such as this liquid rope coiling instability of honey. Standard decoupled methods fail to simulate this phenomena, buckling randomly instead. Unified Stokes solvers, however, create much larger systems, thus leading to higher computational costs. We propose a spatial coarsening method whereby interior cells are consolidated into coarsened supercells, shown here in green. Each supercell is then represented using a reduced model, with velocity defined using an incompressible polynomial vector field. Prior work presented a reduced fluid model with an incompressible affine velocity field, for use with pressure projection. That is, the field is defined with a constant and a linear term, where g is the gradient 2 tensor. Although an affine field is highly expressive, we find that for viscosity, an affine field is insufficient, as shown by this collapsing viscous beam test. Notice that the affine method leads to spurious stiffness relative to the uniform grid method. This motivates extending a reduced fluid model with a quadratic term, where h is a Hessian 3 tensor. We thus define a generalized velocity, v sub b, containing the constant, gradient, and Hessian terms, with a mapping c that transforms them into the usual Euclidean velocity at some point x. To couple the quadratic interior field to the regular grid, we define a transfer operator, j, that transforms the regular velocity degrees of freedom into our generalized velocities. In effect, j accumulates forces from the regular grid and transforms them into generalized forces to be applied into the interior regions. The transpose operation distributes generalized forces into the surrounding regular grid representation. We now have all the tools required to construct our reduced Stokes solver. Starting with a discretized Stokes system, shown here with volume weight suppressed, we apply a reduced model as a simple modification. Notice that this system is simply our original Stokes system, with some degrees of freedom replaced by our generalized velocities. We are effectively solving the momentum equations separately for the uniform grid and the interior regions, with coupling being handled by the j transfer operator. Implementation-wise, we simply use the usual pressure and viscosity stencils, replacing any faces that fall into the interior regions by the generalized variables transformed using j transpose. Performing the collapsing beam test again, we see that the quadratic method more accurately captures the correct bending behavior. Doubling the resolution demonstrates that the quadratic method converges to the expected solution, while the affine method does not. We now demonstrate that our reduced method correctly captures the honey coil effect. And here it is again, with a cutaway view demonstrating the interior regions in green. Thank you for watching.